Hello, I am Mr. Bishop, the Bitmoji guy holding a stack of books right there. This is Chapter 2, Day 6. We're talking about one, none, or many solutions when we're solving systems of equations with matrices. So something that you may or may not have learned in the past in your experience with algebra, when you're solving systems of linear equations, when you have two variables, say x and y, you're going to need at least two equations to be able to solve for both of those variables. So if we've got two variables, we'll need at least two equations in our system to be able to solve for both x and y. And we can understand that graphically, right? So we can think about each equation making a line. So for example, if my blue line looks like this, there's one line, it has its own equation. And then my red line is some other equation, looks like this. And if at some point they happen to cross, well, they cross at one single point, we know that that system of two equations would have one unique solution. And the answer would be the coordinates of that xy point. That would be the answer to our system. So that is how we'd get one solution with our two variables x and y. How would we go about getting no solution? Well, graphically, that would be if we had two parallel lines, meaning they would never cross. Right? In that case, there would be no solution between our two lines, between our two equations. And then the third case, where we could have infinitely many solutions, that would be if I had my blue line somewhere, and then my red line overlapped the blue line, meaning they intersected at all of these points, or an infinite number of points. So if the lines are overlapping, we would have infinitely many solutions. That's easy enough to understand with two equations and two variables, x and y. But what if we had three equations or three variables, right? So let's say we had x, y, z. If we have three variables, we're going to need at least three equations in our system to be able to solve for all of our variables x, y, and z. Now, I'm not that good at drawing in 3D and depicting these things, but I do have a graphic for you that I found. X, Y, Z, you can think of making, instead of a line, a plane, right? A flat plane as a three-dimensional surface here. So this figure shows three planes intersecting at a single point. So that would give us our one unique solution. In fact, the coordinates of that point would be x, y, z. Some other scenarios here. If all three planes intersected in a line, well, all the points on that line would be part of the solution, which means we'd have infinitely many solutions. In the same way that if all three planes flattened out and overlapped each other, well, they would intersect in an infinite number of points. And in the bottom two cases here, notice the planes never all three touch together at a single point. So this one would be no solution. There's nowhere where all three planes actually touch at the same time. In the same case here, right? In fact, none of the planes touch each other, right? They're more so parallel. So that would be another scenario where there are no points of intersection, meaning there would be no solution. Okay, so we can think about the visualizations that way. Let's look at a couple problems from the worksheet and see what it looks like when we get the resulting RREF matrix from these things. So let's take a look at number 18 for starters. We'll go ahead and put that into an augmented matrix, and then we'll run the RREF command in our calculator. And the instructions here say we're looking to see whether each system has one, none, or infinite solutions. So we've been doing this the past couple lessons. I'm going to start with just putting this into an augmented matrix. Right? So I've got my coefficients here, and then my answer column over here. And then I'm going to type that into my calculator for matrix A, and then I'm going to run the RREF command on that matrix. And the resulting matrix looks something like this from my calculator. The first row is a negative 1, 2, 0. The second row is 0, 0, 1. Definitely seems a bit odd already, considering what we've seen up to this point using the RREF command. Let's go ahead and put this back into XYZ form. So that first row would give me negative 1x plus 2y equals 0. And the second row, well, all we have is 0 equals 1, which should give you cause for concern, right? If your calculator prints out something that says 0 equals 1, well, that's a false statement, which means this system has no solution. So right away, right, that should set off something in your brain. Wait, that's wrong. That's a false statement. That means the system has no solution. Okay, well, let's see about number 21 here. Number 21, let's put this into an augmented matrix. So I've got 1, 2, 5 for the first row, 3, negative 1, 1 for the second row. My final equation there looks like I have negative 1, 3, and 5. Reach for my trusty TI-84. I'm going to run the RREF command on this matrix, which is a 3 by 3. And the resulting RREF matrix looks something like this. So I've got 1, 0, 1, 0, 1, 2, and then zeros in the final row there, which does seem a bit odd. But keep in mind, there's only two variables here, x and y. And I told you you only needed two equations to be able to solve for two variables, so they may have just given us more information than we needed. Let's put this back into XYZ form. The first row would just be x equals 1. The second row there, y equals 2. And the third row, in this case, 0 equals 0. That's true, that's great. That provides no further information, as we already know that 0 equals 0. So in this case, we can say that's extraneous, right? That third equation didn't help us much in this scenario. We have our solution already. It's x equals 1 and y equals 2. Or if you'd like it as an ordered pair, that's 1, 2. And as far as the third row goes, yes, 0 does equal 0, but that didn't help us much here. And to further verify, if you remember back from algebra class, you can always check and make sure that this solution is the right answer just by simply plugging it into each equation here, right? So if it's 1 for x and 2 for y, if I plug it into the first equation, that's 1 plus 4 gives you 5, bingo. 3 minus 2 equals 1, that checks out. Last equation there, negative 1 plus 6 equals 5. So you can verify it. It works for all three equations. Our solution is 1, 2. All right, so we've seen an example of no solution. We've seen an example of something that's just got one solution. Maybe the next one will have infinitely many solutions. How about we take a look at number 27 here? I'm going to start off the same way. Let's put this into an augmented matrix. So I'm going to get my coefficients here from my x's, my y's, and my z's all nice and organized. And then my answer column there. Go ahead and grab my calculator and run the RREF command. This is a 3 by 4 matrix, 3 rows by 1, 2, 3, 4 columns. And the resulting RREF matrix looks something like this. This is what my calculator printed out for me. And this is starting to look a little weird again. Before we answer the question, we've got to put this back into XYZ form. So that first row there, we've got 1x plus 1z equals negative 6. The second row, we just have 1y equals 5. That's easy enough. The third row, again, 0 equals 0. That's great. Doesn't help us much in this case. Right? That's nice that 0 equals 0. Again, extraneous doesn't do much for us. Looking at our two equations that we did get, though, you notice y equals 5. That's nice. But what do x and z equal? And right now, you can't give me a firm answer. What two numbers add up to give you -6? I could think of all sorts of combinations, right, for x and z. The point being that when we got this system into reduced row echelon form, this is as far as it could be reduced. And now we are stuck, right? And we are stuck for infinity in this case because we can't narrow down what x and z are. And if you find yourself in this scenario where you've got remaining variables and you don't have the solutions for all three, this is a case where we have infinitely many solutions, right? I bet you could think of a few examples yourself about what x and z could be that are just numbers that add up to -6. They could both be -3, for example. One could be -5, the other one could be -1. Technically, there is an infinite number of possibilities at this point. So when we get to this stage in our RREF matrix, now we've got an example of what infinitely many solutions would look like. All right, and I'll do one more with you on this video, and then I'll leave the rest to you. So 37 and 38 look a little bit different, right? It says we're supposed to give 3 solutions to the system. Well, how do we know there's 3 solutions? What if there's just one unique solution, right? Well, if you look at either scenario, 37 or 38, both of them feature 3 variables, x, y, and z, yet they only have 2 equations, right? Which means we're going to be stuck either way, and we're going to have infinite solutions. All right, that's great. If you're telling me there are an infinite number of solutions, fine, I'll buy that. But then you should be able to give me at least 3 of them, yes? Right? You're telling me there's infinitely many? Just give me 3. Give me 3 of those solutions. So we're going to start off in the same fashion. I'm going to do number 38 here. So I'm going to take this and put it into an augmented matrix. There's my first row, 1, 5, 3, 9. There's my second row, 2, 9, 7, and 5. Again, grab my handy TI-84, and I'm going to run the RREF command, which gives me 108, -56, 01, -113. That's what my calculator printed out from the RREF command. Makes me a little bit uneasy. I wish I could tell you right away what x, y, and z are equal to. But again, 3 variables and only 2 equations. That wasn't going to be the case. So to move forward, we need to put this back into x, y, z form. So read that first row and put that into x, y, z form. We've got 1x plus 8z equals -56. The second row there looks like we've got 1y minus a z equals 13. Okay, and that's the reduced row echelon form. So at this stage, right, this is it. That's what we know the relationship between x, y, and z to be. And there's an infinite number of combinations you could pick. So to help you, there's tables for each of these questions. You can plug in whatever number you'd like into whichever variable you'd like and figure out the rest of the variables. Well, I think it'd be smartest to choose z. Why don't we plug in values for z? And again, you can pick any values you want. I'm probably going to pick some easy ones. But since z is in both of the equations, it just seems like it would make our life a lot easier if we plug in some easy values for z and see what the answers are. And again, if you want to do it the hard way, be my guest. Plug a value in for x, solve this for z, and then plug that z value in here and solve this for y. Sure, go right ahead. Right? But I'm going to make this a little bit easier myself and plug my answers or my starting values into z. So for example, I said I'd keep it easy, right? What happens when z is, say, 0, right? What's x and y? What happens when z is maybe 1, right? What's x and y? what happens when z is maybe 2, right? I told you I was going to pick some really easy values here. What are x and y? So you should be able to give me the ordered triple for each one of those. For example, if you plug in 0 for z, right? Plug a 0 in right here. Well, y minus 0 is 13. Plug a 0 in for z here. X plus 0 is negative 56. So that would be one ordered triple. That's one solution. How about plugging 1 in for z? You plug a 1 in for z in the bottom equation, that gives you y minus 1 equals 13. What number minus 1 gives you 13? Y is 14. Plug a 1 in up here. X plus 8 equals negative 56. So if you subtracted 8 from both sides, you'd get negative 64 for x. And last but not least, if you plug a 2 in for z right here, what number minus 2 gives you 13? Well, that'd be 15. And if you plug a 2 in for z here, it'd be x plus 16 equals negative 56. So if you subtract that 16 from both sides, you get x equals negative 72. So there are your 3 separate solutions, your 3 ordered triples. And we can easily get those just by plugging in values for z and seeing what x and y are based on those values. Again, we knew there would be infinite solutions going into this example, right? We just had to find 3 of them within this table, right? So I picked easy values to plug in, and I chose to plug them into z since z was already in both equations, making our lives easier. All right, so we've talked about what it looks like to get one, none, or many solutions based on the results of our augmented matrices. That's all for this video. Thanks for watching.